Hello, Calc 2 students. Here is section 9.1, part 2. It's a big section. In this part, we discuss the definition of a monotonic sequence. There's two types. You could have a sequence where the a sub I satisfy these inequalities. You and I might want to call this an increasing sequence, but your book is being very particular and saying it's called non-decreasing. There could be some reason for that. Notice with all these or equals here that this could be a constant sequence. Would you call a constant sequence an increasing one? No. Or you could have a sequence that's increasing on some terms, but then it maybe level offs for a while and then it's increasing again. So that would also be included in a non-decreasing sequence. So a monotonic sequence could be non-decreasing if it satisfies this set of inequalities, or it could be non-increasing if it satisfies this set of inequalities. You might want to call this decreasing, but again, the or equals allow that it could be constant on some points and then decreasing again, or constant all the way through, still be considered non-increasing. So it includes a lot more than just an increasing sequence or a decreasing sequence, right? Some examples of a non-increasing sequence would be 1 plus 1 over n. So n equal to 1, n equal to 2, n equal to 3, n equal to 4. You could convince yourself these are equal to 2, 3/2, 4/3, 5/4. It's non-increasing because, in fact, it's decreasing. B sub n, which is included in non-increasing. How about b sub n equaling 3 over the quantity 1 plus 1 over n? What's in there? Well, I guess when n is equal to 1, you've got 3 divided by 1 plus 1, so that's 3/2, but what about the rest of it? So as I was trying to show you in the on Cisco WebEx earlier today, but failing massively with its crayon smudged visuals, that you can calculate a bunch of terms in a sequence much more quickly by stepping the process using a table and calculating not across, that takes forever, but by columns. So for a bunch of n values, 1, 2, 3, 4, 5, we could first calculate the 1 over n part. 1, 1/2, 1/3, 1/4, 1/5. Then we could calculate this denominator, 1 plus 1 over n. Well, that's 1 plus 1 to 2 plus, 1 plus 1 over n is 2 here, but it's 1 plus 1/2, 3/2, 1 plus 1/3, 4/3, 1 plus 1/4, 5/4, and so on. And then we could, if we write this as a improper fraction, easily take its reciprocal. So reciprocal of that is 1/2, reciprocal of that is 2/3, 1/2, 2/3, 3/4, 4/5, 5/6, and then just multiply the numerator by 3. So now we have 3/2, or 2, or 2 1/4, or, so you can stop the video if you like and follow how I'm getting these quantities, that b sub n's look like 1 1/2, 2, 2 1/4, 2 1/5, 2 1/2. So it's not decreasing because it is increasing. All right. I'd like to point out that sometimes we're going to run across sequences that are eventually, what I call eventually monotonic. For example, I could take that sequence up here, 2, 3/2, 4/3, 5/4. Can you see it? One up here. And let me just stick on some oddball terms in the beginning and define a new sequence. Let's say this sequence starts out like 0, 1, 2, and then 1.5, 1 1/3, 1 1/4, 1 1/5. So it's not monotonic until after the third term. Before that, these are increasing, then they start decreasing. So we will say in the tail here, this is acting like a monotonic sequence. But is the whole thing monotonic? No, because we're not satisfying these inequalities in the definition in the first few terms. Got to have all these inequalities true for it to be non-decreasing or non-increasing, to be monotonic. Okay. We also define in section 9.1 a bounded sequence. Actually, there's 3 definitions going on here. We say a sequence is bounded above if there exists some number m such that a sub n's are all less than or equal to that m, and that's true for all indices n. Or we say it's bounded below if there exists some number n where the a sub n's are all greater than or equal to that. But we only say it is bounded if it is bounded both above and below. Some examples. 1 minus 1 over n. Let's see, what does that look like? For n equal to 1 here, we've got, it's 0. For n equal to 2, it's equal to 1/2. To n equal to 3, it's 2/3. So on. So what am I getting? 0, 1/2, 2/3, 3/4, 4/5, 5/6. This sequence is bounded above by 732, right? Every term in here that you're going to see is going to be less than or equal to 732. You could also say it's bounded below by -3 million. Every term in there is greater than or equal to -3 million. So for sequences, if you find a bound and upper bound, there are infinitely many other upper bounds. If you find a lower bound, there are infinitely many other numbers that would also serve as a lower bound. Now, you might have been looking at this and thinking that 1 is its bound. 1 is just one of many upper bounds, but it is a special upper bound. It's what's called the least upper bound. LUB, sometimes you'll see that. LUB, the least upper bound, is 1 for this sequence here. 0, 1/2, 2/3, 3/4, 4/5. This thing is converging to 1. It's never going to hit it, right? Because n is, for all numbers, this 1 minus 1 over n is going to be less than 1. So 1, but turns out to be, of all the upper bounds, it's the least. What about all those lower bounds? You know, -3 million being a lower bound, being kind of facetious. You could say that 0 is the greatest of all the lower bounds. Yes, 0 is its GLB, greatest lower bound. But if somebody asks you for a bound, you're as free as I was here or there. Upper bound or lower bound, just pick any number that satisfies the property. So is this sequence bounded? Yes, it has both an upper bound and a lower bound. So this sequence is bounded. How about this one? 3 to the n over 2 to the n. What does it look like? 3/2, 9/4, 27/8, 81/16, ... It's bounded below by 0 or -1 million, negative a googol. There's infinitely many lower bounds. But it is not bounded from above, as it turns out. We're going to find out that the limit of 3 to the n over 2 to the n is going to turn out to be equal to plus infinity. So successive powers. So what's going on here? You could look at this as 3/2 raised to the nth power, right? So each time we go to a successive term, we hit it with another power of 3/2, which is 1.5. You multiply something by 1.5, you make it bigger, right? So successive powers of a ratio that's greater than 1, that's going to increase without bound. So because it's not bounded from above, even though it's bounded from below, we say the sequence is not bounded. Now, why do we care about whether a sequence is bounded or whether it's monotonic? Because we have a big tool that we use quite a bit, and that's theorem 9.5. It says if a sequence is bounded and is monotonic, then it converges. It doesn't tell you what it converges to, but it tells you there's some real number that the limit of the a sub n's is going to approach. We use this a lot. Again, it doesn't tell you how to construct it. It just tells you it has some limit. Now, the proof of this, we're not going to go into. You can read it. It uses something called the axiom of completeness of real numbers. What do they mean by that? Well, the best way to quickly understand that is to notice that another set of numbers, the rationals, is not complete. What do we mean by being complete? Look at this sequence of rational numbers. 3, 3.1, right? That's 31 divided by 10. 3.14, that's 314 divided by 100, right? These are all rational numbers, ratios of integers. 3.141, 3.1415, 3.14159, 3.14159, etc., etc., etc. In other words, this is a sequence of more and more accurate decimal approximations of pi. So p sub n is converging to pi, but pi is irrational. It's not rational. So you can have a sequence of rational numbers that are converging to something that doesn't belong to the rationals. So that we would say the rationals are not complete because they have a bunch of holes in them. Here's another example. 1, 1.4, 1.41, 1.414, 1.4142, 1.41421, ... This is a sequence of approximations to the square root of 2. The square root of 2 is also irrational. It doesn't belong to the rationals. So this sequence is converging to something that doesn't belong to the set of numbers from whence it came. But the real numbers are complete. And the proof of theorem 9.5 depends on that. So if you have a sequence of real numbers that is bounded and that are monotonic, then you can prove, and you can look at the book's proof, you can prove that the sequence has to converge to some real number. Now notice that this is a one-direction implication. It says if it's monotonic and bounded, you're guaranteed it's convergent. However, that does not say that a convergent series is not always monotonic. Let's look at some examples. This guy, -1/2 to the n. It bops back and forth, positive, negative, -1/2, positive 1/4, -1/8, positive 1/16, ... But this guy this sequence is convergent by theorem 9.4. Remember that from the first video about section 9.1. If you look at the absolute value sequence, 1/2, I take the absolute values of all these, 1/2, 1/4, 1/8, 1/16, that's converging to 0. If the absolute value sequence is converging to 0, then by theorem 9.4, you can rip off those absolute value signs and say it's also converging to 0. So this one is oscillating around 0, but it's still converging to 0. It's not monotonic, and yet it is convergent. Here's another one. 1 plus -1 raised to the nth power. Isn't that the same? No. I'm adding a 1 to each of those terms. So 1 plus a -1/2 gives a 1/2. 1 plus a 1/4 gives me 5/4. 1 plus a -1/8 gives me a 7/8. What's going on here? 1/2, 5/4, 7/8, 1/16, 1 minus a 32nd, 1 plus a 1/64, 1 minus a 1/128. It's oscillating around not 0, but it is converging, it is oscillating around 1. And we will show that this converges to 1, but it's not monotonic. It is true that if it's a convergent sequence, it does have to be bounded. Not going to go into that proof, but that is true. But you can be a convergent sequence and not have been monotonic. So here is the thing you're going to have to send me an email about to prove that you've watched this video. Okay. Look at problems 54, 56, 58, and 60, those sequences in section 9.1. Which of those have monotonic sequences? Which of them are bounded? Which of them are convergent? Are they convergent by theorem 9.5 or by some other theorem maybe? I'd like you to hand these in. Email me about these. Send me an email to show that you've watched the video, and do as much as you can on these problems, okay? Use it as a learning opportunity. Don't worry, you're not going to be graded on those, but just handing in 54, I don't know, 56, I don't know, 58, I don't know. Yeah, that's not going to work. Show me that you have been listening to the definitions and the examples of monotonic sequences and bounded sequence. Try your best. That's it.